I'm from the perspective of a gravitational string theorist.
Hi, I would like to begin by thanking the organisers for the opportunity to speak and to interact with all of you. I have a website up there where you can download any of the slides should you be interested. So just to start off with a little old joke that science students tend to tell among themselves. Physicists think of ourselves as sort of, the most pure of the scientists. After all, chemistry is just applied physics, and biology is just applied chemistry, and so forth and so on. And then the joke goes that, oh well, hey, mathematician says, I didn't see you guys all the way over here, far further along the purity axis. Well, one of the things that I've become aware of being here yesterday and so forth is that, well, then there's these philosophers over here who are saying, should we tell them? So that just this funny is just intended to give you the idea that I'm actually really open to learning from philosophers. I'm not a very good one. I have quite considerable ignorance on philosophy, and so I'd like to apologize in advance for that, but feel free to teach me. So what I would like to do is to break my presentation into 4 approximately equal pieces. You can follow along to see when things are going to change by following the sections up here. Each of them has approximately 5 or 6 slides. And so that means I'll be spending about 12 minutes in each of them, in each of the sections, discussing some of the issues. So I want to start by saying some words about framing the question, what is quantum gravity? Again, from the perspective of a gravitational theorist. A gravitational string theorist. I am not any other kind of gravity theorist, so I can just talk from this perspective. And then I'll move to giving you a little bit of an overview of many of the interesting questions that were raised at the Strings 2014 conference, which I and a couple of my graduate students went to in Princeton in the summer last year. And to give that as a way of jumping into developing the 2 main themes that I'd like to talk about and on which I've worked myself, but I'm not only going to talk about my own work, I'd like to try to summarize some of the really interesting questions that are coming out of building microscopic models of black holes and also ADS-CFT holography that are between them, enhancing the links between classical space-time geometry and quantum entanglement. So, as I said, curiosity about physics, and especially gravity, is my prime driver, so educate me where necessary. I want to start off by making clear that I'm not one of those physicists like Stephen Hawking who made headlines recently claiming that philosophy is dead. This felt like trolling, basically, from somebody with relatively little investment in philosophical expertise. The other Steve Weinberg, is perhaps the one whose quotation you should be a bit more worried about. His criticism carries more weight, as he is, unlike me, far from ignorant about the philosophy of science. And he said to know of no one who has participated actively in the advance of physics in the post-war period, meaning World War II, whose research has been significantly helped by the work of philosophers. Ouch. But my point I would really like to ask is why? And maybe is some change necessary? Do physicists need to listen to philosophers more? I'm not sure. But one thing that is fairly clear is that physicists are generally in a fairly blazing hurry to understand new phenomena and explore the utility of tools, whether they're theoretical tools or experimental tools. We know that mathematical rigor tends to take longer to establish. For example, many mathematicians are still not happy with the Feynman path integral, but physicists continue using it willy-nilly and getting some pretty interesting physics out of it. A historical example that's fairly famous is of the Dirac delta, which physicists used for years before it was understood mathematically as a distribution. Perhaps the philosophical interpretation might lag even further behind. One of the frustrations I often hear from physicists is, why are philosophers still arguing about that? Well, that's a question that I don't pretend to know the answer to, so I'll just leave that in the environment there. But in quantum mechanics interpretations, I think many of us would pick decoherence as a way of thinking about it. That does require thinking about a multiverse, but that's not terribly upsetting for some of us. But the point I want to end with on this slide is just all researchers who teach know there is a mismatch between the historical development of a subject and the most efficient way to teach it. And a question that I find interesting is, why do we all sometimes wallow in confusions that are resolvable by adoption of superior conceptual technology? Next, I'd like to say just a wee bit about aesthetics. Interdisciplinary interactions, like we're attempting here, can be a little uncomfortable because constructing a dictionary of motivations which often seem kind of orthogonal at first, can be time-consuming. And how can physicists and philosophers be maximally useful to each other, if that's the criterion? I think true interdisciplinary interactions gives both parties measurable benefits. But what about aesthetics? Well, physicists don't like to think we interface with fashion very much. You can tell by looking at me. But fashion in physics is also culture-dependent, and it's fluid. The aesthetics are fluid. What is sexy today might not necessarily be sexy 3 years from now. And theoretical physics timescales are short, perhaps too short. It makes us a lot in a hurry. It used to be that, for example, publications either side of the Iron Curtain were considered simultaneous for as far as ongoing credit was concerned, if you published within a year or two, maybe 3. Now, with everything put online in the archive preprint server, you get more like 1 or 2 weeks, or maybe 3, if you want to be considered to get the result that you were chasing simultaneously with another group. I think concerns about employability among the precariat in physics, people with non-tenured positions, for example, limits their options for career strategies, and the publish or perish ethos makes incrementalism in theoretical physics strategic and speed essential. People are just in a really big hurry to produce results. And I've seen senior string theorists who tend to advise younger colleagues not to try to think deeply or philosophically about the nature of space and time, because that generally takes quite a long time, and you may not have enough time in order to establish a physics credible record on your CV in that short amount of time. And I think David Gross's maxim, when in doubt, calculate, kind of reverberates around the world. The idea that if you're trying to construct a model, that's all very well, but if you have a model that's sort of like the problem you want to solve, just get that and calculate and do something rather than trying to spend a lot of conceptual time coming up with the right answer. So I don't know what the right theoretical physics aesthetic is. Is it utility? If it's utility, is it experimental or theoretical? Is it beauty? Is it mathematical beauty? What other kind of beauty is the thing that drives people to develop all this stuff? So in string theory, like in any other field, we're judged sensitively on our taste in selecting problems on which to work. But an interesting question is that how exactly do we teach what constitutes good taste in theoretical physics? Like what's good problems to select, without arguing from institutional authority? Oh, all the Stanford people are doing it. That must mean it's really interesting. Or all the Princeton people say this is really important, so we should all be working on it. I don't mean to say that theoretical physicists are just, people who get physics memes and go with it. But there is a speed to it that I think discourages a certain amount of philosophizing. But what is quantum gravity from the perspective of a string theorist? So in his Beyond Spacetime 1 talk, Jeff Harvey remarked that loop quantum gravity people have roots in GR, and these guys tended to like philosophizing. String theorists tend to be a bit more pragmatic. A little bit like the Caltech interpretation of quantum mechanics. Who cares what the interpretation is if it works? That's perhaps a little strange for a philosophical interpretation, but for physicists it's pretty common. And for all people who use high-energy theoretical physics techniques, theoretical physics, string theory or particle theory, we use the Wilsonian renormalization group framework to think about the universe. And in that point of view, general relativity is known as an effective theory, like the Fermi theory of weak interactions, that works at low energy. But as far as we know, according to the renormalization group, like QED, general relativity doesn't exist in the ultraviolet. It's a wonderful, mighty fine classical theory of gravity, but it's got to be replaced by something at high energies according to the Wilsonian RG. Now, you can't just decide to give up the Wilsonian RG as a way of thinking about the universe in quantum physics, because it's the bedrock that underlies a lot of experiments in condensed matter and other parts of physics, not just particle physics. So, what does the Wilsonian RG do? It tells us exactly how the couplings of your theory become different, how they change as you change your coarse graining. As you drive the coarse graining finer and finer, going up to higher and higher energies, the couplings will run. So then, within the framework of string theory, if you're trying to construct a theory of quantum gravity, the hard part is actually connecting the ultraviolet physics, the very high energy physics that we think we understand because of quantum constraints on the theory. Internal self-consistency tell us that we can have some confidence about doing physics up there. But the infrared is where the phenomenology is that we need to explain theoretically. So the middle ground is really the difficult terrain, trying to marry the bottom-up motivations to say what is quantum gravity looking like from what we can see in experiments we can already do, and string theorists are trying to work from the top down, saying, well, I've got this theory of quantum gravity that makes sense in the ultraviolet, and it's easy to calculate with up there, but then the difficulty is connecting with the phenomenology. So being a string theorist doesn't preclude having bottom-up motivations, but many of the most influential string theorists have them. But it's a little difficult to be trying to be a gap bridger. It's a bit like trying to style yourself as equal parts mathematician and physicist. You tend not to get hired either by the math department or the physics department. People tend to want to see a weighting that's, you're putting most of your eggs in one disciplinary basket. So what is the approach that string theorists use to get started with microscopic models? And that's the story of the string world sheet. You may ask, and I think this is also a very interesting question, is there a unique quantum continuation of general relativity? GR is a really great classical theory of gravity. People are working on different ways of quantizing it, which seem to give very different looking degrees of freedom and kinds of physics. But maybe in the end, all our various different approaches will end up converging to the right quantum gravity. We just don't know yet. But as such, each approach to understanding what quantum gravity is and how time might emerge, for example, each practitioners of each approach, including string theorists, are keenly aware in the current limitations in our ability to answer that correspondence principle question. Can I show that my theory of quantum gravity, actually in a classical limit, reduces to what we already know enough from Einstein's general relativity? So how do you get started even writing down an ultraviolet theory for string theory? I believe this was something that was introduced by one of the speakers at Beyond Spacetime 1, so I'll just mention it very briefly. You've got to describe matter and spacetime both in the same equation, because string theory unifies those things under one rubric. So how do you begin? You write down this thing called the single model world sheet action. It really just says that the action principle is like an extreme surface thing as the string moves through space-time, and you minimize the area functional of that world sheet. And that treats background space-time fields, including the graviton, as coupling functions. And that classical theory has two-dimensional conformal invariants. Classically, the Nambu-Goto or the Polyakov action are conformally invariant. They have other symmetries as well. But insisting that that powerful two-dimensional conformal symmetry, which has an infinite number of generators, so it's a really powerful and really constraining symmetry, if you insist that that conformal invariance persists at the quantum level, that requires all the beta functions of all those constants, the beta functions being the things that tell you how the couplings run with energy, have to vanish. And there's one of those equations for each of the space-time fields, and those are the space-time equations of motion. So that's how the classical limit comes out in string theory. Some people like to say string theory bakes in a Newtonian limit at the outset. The disadvantage is that we end up with 10 dimensions of space-time, which is the wrong number for what we see in front of us, and we also end up with some other massless field in the spectrum, like axions and dilitons, and figuring out how to get rid of those from the spectrum so that they aren't in conflict with Fifth-Morse experiments and so forth. That's part of what I mean by when it's hard. Now, some of the critics who were talking about string theory and its lack of background independence say that, well, it just perturbs about a background, and that background is fixed. It's actually not entirely true. Fluctuations of the background are included in the analysis, as Jeff Harvey said in his talk in Beyond Spacetime 1. So string theory actually has a bit less naive form of background independence than many people think. But it's also a very interesting question to ask, what form should background independence even take when there is no neoclassical regime? If you're in a thoroughly quantum regime of your field theory, how do you know what background independence should look like? I don't think that's obvious. I would reckon that superstring dualities, which came a full decade after people worked out how to do the quantum theory of strings in the ultraviolet using the sigma model technology, which launched the first superstring revolution. But in the second superstring revolution, you ended up finding that physically radically different systems with very different looking degrees of freedom ended up to be equal to each other, two physical systems having the same underlying physics. And if you want a review of superstring duality, supposedly for philosophers and historians, then there's a rather good article by Musings that I can recommend. But if you're talking about ADS CFT, which came even later than the superstring duality by a couple of years, 2 or 3 years, we don't know how to do the world sheet theory in an anti-de Sitter space of strings. So we don't even have a sigma model there, but we can still learn what quantum gravity is with anti-de Sitter boundary conditions by using the conformal field theory to define what quantum gravity is for that situation. So, string theorists have quite a few techniques, and the world sheet isn't the only one of them. Now, if I'm a string theorist and I don't talk about testability, I really do need to say a little bit about that. So string theorists are famously testy about the testability of the theory. So I will just state my position fairly clearly. But if you work to build compactifications of string theory that are suitable for making a universe with the standard model, perhaps plus some other stuff, perhaps at LHC energies, and with a small positive cosmological constant, led to this incredibly large landscape of vacua. 10 to the 500 possible amounts of numbers of vacua, and that rather spoiled string theory's dream of being predictive about getting our universe rather than, say, some very different looking universe. But it's a really important point that many people don't know is that Kummerbuffer pointed out over 10 years ago that for particle theory, he called their version of the landscape the swampland, all the possible vacua of particle theories, is actually the swampland is even larger than the string theory landscape, because particle theories have fewer ultraviolet constraints. And so competitors who lecture us on predictability aren't really standing on clearly superior ground. If you want to hear an example of somebody lecturing at string theorists about predictability, you can listen to Paul Steinhardt's talk about strings 2014. That's enough comment on that for now. Another small myth that I would like to blow up just in the next minute is some people claim that string theory is not falsifiable, that you have to take it on as a frame myth, it's a way of thinking, it's not something that you can test in an experiment. They're actually wrong. And I'll just give you one counterexample when you need is one, which is a nice paper written by Jacques Dissler and Ben Grinstein and Raphael Porto and Ira Rothstein, where they showed how, for example, in doing some experiments with WW scattering, you could indeed falsify string theory in important ways. But, that's a discussion really for another time. We're not talking so much about the theory of experiments bridge in physics. We're talking about the theoretical physics philosophy bridge more. So I'll just introduce my last comment before I start talking about the more technical stuff, which is to talk about what I think is the most compelling intellectual argument in favor of string theory, is it's, apart from its utility in doing a lot of things, not everybody thinks utility is the primary criterion, it's the interconnectedness with other parts of physics and cognate disciplines. As a field, string theory has always had porous boundaries, both when it was out in the wilderness when it was not trendy, when only a few people were doing it in the 70s and early 80s, but then when it was also trendy, it's also had fairly porous boundaries. You know that string theory is a heavy end user of math, but it also has driven developments in math, so it's not really an interdisciplinary dilettante. String theory is famous in terms of this interconnectedness among beginning graduate students for having a very large toolbox to master. Often our young students get frustrated with how long they have to spend learning the basics before they can really get stuck into research. So there's a theorem attributed to Steve Schenker at Stanford, where it goes that aspect of theoretical physics which you least enjoy learning about and using is that which you're going to have to learn tomorrow. And it happened to me recently that when higher spin became really trendy, I had to learn about W algebras, and I hadn't really been wanting to learn about W algebras, but you get over it. So some of the major themes that have been in string theory in the last couple of decades is, yes, model building for LHC and cosmology. The cosmology part was really big because we had to find out ways to make vacua of the small positive cosmological constant when the data became really clear at the end of the 90s. Developing formal aspects of string theories and also SUSY gauge field theories and conformal field theories. There's been an amazing amount of new amplitude technologies discovered for both quantum field theories and string theory. Many new gravity solutions available in higher dimensions, useful for building black holes and black brains and things called fuzzballs, which I'll talk about later. And then ADS-CFT dualities between string theories and quantum field theories, and building microscopic models of black holes. So I think these two themes that I've highlighted, which I'll expand upon after I mention the big questions from Strings 2014, these are the two places where there's a lot going on regarding answering the question, what is quantum gravity? And how might we address a question of where time might start, and if we can't talk about emergence of time, let's talk about emergence of space, maybe with weak time dependence. That's less difficult than doing a strong time dependent situation like creating time out of nothing. So that's why I want to focus on these two, because I think they're the most relevant to the question that you're asking here, about the nature of time and quantum gravity. I just mentioned parenthetically that David Gross commented at the Strings conference in his vision talk about what he thinks is a measure of the health of the field, is how many of the talks at the Strings 2014 conference in Princeton and at the Institute for Advanced Study were formal string theory topics, and how many were actually about something else, like applications of use to other physicists or mathematicians. And the answer is that most of the talks were actually not very formal. So take it as a, I don't know if that makes string theory a healthy field or not, but let me say a little bit about what happened at the conference. That's relevant to the question of quantum gravity. You can watch videotapes of all of the talks that were given, and there was a very broad list of topics that was featured. For example, renormalization in string theory, the conformal field theory bootstrap, instabilities of ADS, global ADS, astroparticle experiments, inflations and axions and string inflation. People talked about firewalls, holographic entanglement and geometry, entropy bounds, entropy inequalities in quantum field theory, fuzzballs, and this higher spin. Higher spin, by the way, is a very interesting idea where you have not just a graviton, and you don't have a full string theory, but you do have a graviton with a whole bunch of higher spin modes in a tower that can make sense in anti-de Sitter space for some situations. This might be a bridge between just gravity and doing full string theory, which is one of the reasons why people have become quite interested in it. There was also discussions about holographic modeling of condensed matter systems using ADS-CFT, non-perturbative aspects of what's called APJ-M theory, which is to do with a particular highly supersymmetric configuration of M-theory D-branes, and talking about topological aspects of Susy gauge theories. Don't worry, I'm not going to talk about any of these more mathematical topics. There was also more on aspects of Susy gauge theories, gravity duals of higher dimensional conformal field theories, mathematical string theory, a lot about amplitude technologies, and then mathematical aspects rounded out the conference and 5 vision talks. But the point why I'm bringing up the conference is something really neat that Andy Strominger did before his talk, which is to poll a whole bunch of string theorists. There must have been dozens of us on his distribution list, because 74 people sent in answers, some of which I'll show. He asked what people think are the key questions about string theory as a theory of quantum gravity. And I'm going to give you a little selection of some of these questions as an indication of what people in the field are thinking about quantum gravity questions. Like what kinds of questions are really interesting string theorists at the moment. They may not be the same questions that are interesting to causal set people, but if we cross-fertilize, then we might discover that other people are doing things that we're interested in too. So I learned a lot by listening to the causal set talks yesterday, for instance, as well as all the rest of them. So John Schwartz asked, is there a formulation of M theory without reference to space or time? If so, what's the role of quantum entanglement? And this sort of started a theme that surrounds the idea of space-time emergence. Really, they usually mean space emergence, but we hope to eventually get to the question of time emergence as well. Nathan Seiberg asked, what is time and how does quantum mechanics emerge? Given that space is emergent, so should time be. But since it's difficult to formulate quantum mechanics without time, quantum mechanics itself should be an emergent theory. Ashok Sen asked another angle on that question, what's the precise relation between quantum entanglement and classical geometry? Dan Friedman asked, how much further can the present hints of a relationship between entanglement and dynamical gravity be developed? Hiroshi Oguri asked, how can you tell if a low-energy effective field theory, like gravity, cannot be completed as a consistent quantum theory? The gravity as the weakest force conjecture is a good example, but maybe we could derive other counterexamples to folklores motivated by string theory. Lenny Susskind, my PhD thesis advisor, asked a question about the black hole information paradox. What are the big principles we are missing whose absence prevents us from giving a definitive resolution? And he thinks many of the answers will come from the connections between gravity, i.e. classical space-time, and quantum information theory. In particular, entanglement theory and computational complexity. And we'll get to why he thinks that later on. Elias Karitsis asked, is there a way to prove the quantum field theory string theory correspondence? Takinagi asked about what's the entropic meaning of internal spaces in anti-de Sitter, like ES5 and ADS5 times S5, and how do those emerge holographically? Joanna Ertmanger asked a more experimentally oriented question, asking, using gravity gauge duality, can you make predictions for universal properties of interesting observables, like things that you measure in heavy ion collisions at REC or in the LHC, or modeling condensed matter? Matthias Gabriel asked, what is quantum gravity in 3 dimensions? One of the reasons he asked that is he's been developing one of the most interesting questions about what's going on there. What's his name? Mikhail Vasilyev asked what's the exact relation between higher spin and string theory. Simona Giombi asked, do higher spin gauge theories define consistent theories of quantum gravity in general space-time dimensions? And if so, are they always related to some string theory? Juan Malacena, the one who's famous for inventing the ADS-CFT correspondence, asked what is the general theory of weakly coupled interacting higher spin particles Is string theory the only solution, just like general relativity is the only solution of a similar question involving massless spin-2 particles and to leading order and derivatives? Rastelli asked a more general question: what are the universal constraints from symmetries, analyticity, and unitarity on the S matrix for quantum gravity? And Berkovitz asked, Berkovitz asked a more technical question about, can twistors be used to simplify string theory in a similar way as the original idea of CFD field theory? There were a bunch of more formal aspects. Maybe I should not go through quite too many of them because I've expanded a bit too much on my time earlier. But there's a whole bunch of really interesting questions also on the formal aspects of string theory, probably a bit too technical for this audience. But I'll finish with the comments that were made about black holes and cosmology, because they're a bit closer to my heart. Joe Fortinsky, who was one of the people who ignited the firewall controversy about the effectiveness of general relativity around black holes, asked, do all black holes have smooth interiors? Eva Silverstein asked what I think is a super interesting question: at what level does perturbative string theory lead to a breakdown of effective field theory in time-dependent systems, like naturally formed evaporating black holes? And does this generate sufficient non-adiabatic effects to address the firewall problem? One person asked, why is the entropy of most black holes captured by a Cardi-like formula? Nick Warner asked, are there large deviations from the predictions of general relativity at the horizon scale of a kind of black hole that lies in the core of some galaxies, like some million solar mass near extreme Kerr black hole? We are very far from being able to make you an honest-to-God microscopic model of the astrophysical black holes, but we've worked with more like a Lego set of string theory tools that allow us to build something that looks a lot like a black hole, but it has some special properties that makes it not realistic yet. Busso asked, what is quantum gravity in a space-time without boundary, like a closed universe? That was Raphael Busso. Mark van Ramston asked, what's the Hilbert space and entanglement structure of a quantum gravity state representing a cosmological space-time, for example, de Sitter, or some eternally inflating multiverse? And Finn Larson asked about the microscopic origin of de Sitter entropy, and De Boer asked whether the non-locality of quantum gravity might have any implications for cosmology, and David Kudasov asked a kind of a cheeky one, is the relation in string theory between SUSY breaking and cosmic acceleration? At any rate, I hope that, I mean, it might have been a little bit too much information too soon. Don't worry, it's not going to be on the exam. I just wanted to give you a little bit of a sense of what do the big minds in gravitational and string theory with an interest in gravity. Not all of them have a particular interest in gravity, but of the ones that do, we can see that there were really 4 themes emerging out of these big questions that were featured at the final parts of the Strings Conference. And that was about space-time emergence and the role of quantum entanglement, the story of holography and higher spin, formal aspects of string theory, and black holes and cosmology. So I'm going to run with 2 of the themes to try to give you a sense of what people think are interesting recently. I'm going to, 1 out of 6 of each of the slides is going to have a commercial for the kind of research that I actually work on myself, to give you an indication that I actually do write papers as well as try to summarize gravitational string theory. So what have people been doing with using string theory to build models of black holes microscopically? So as you know, Stephen Hawking, just over 40 years ago, taught us that Hawking quanta that are emitted by black holes don't carry information about anything behind the horizon other than what you can measure out at infinity, the alien mass and angular momentum and any gauge charges you might have. Now, the thing you may not know is a theorem proved that by Samir Mathur in 2009 that subleading quantum gravity corrections, in other words, doing just small quantum corrections about semi-classical space-time, cannot actually resolve the black hole information paradox. Only order 1 corrections to semi-classical black hole expectations around the horizon can actually rescue unitarity. And so that means if we're going to be able to work out how to resolve the information problem, we're going to need lots of hair on our solutions to be able to memorize all the information about what fell into the black hole. But the question is there any? You may know that there are things called no-hair theorems in 4 dimensions. Those theorems are always derived by assuming a particular form of the Lagrangian and then finding out whether or not you can have hair of that type on a black hole. The intuitions that people have built up from working in 4 dimensions and fewer on gravity theories turned out to be pretty far wrong for applications to higher dimensions. In 5 dimensions and higher, for example, there are black ring solutions available, which have a horizon topology of more like a torus than a sphere, for example. And that gives us a much wider variety of solutions available as ingredients for building black holes and black brains and other kinds of spacetimes of interest. Joseph Benner and Nick Warner have done a huge amount of work on this and their collaborators, and there's a rather nice review available at that particular location. So, you know, D-branes are the objects that allowed us to count the Bekenstein-Hawking entropy of the black hole. You've all heard it, so I'm not going to insult you by saying it again. But I want to just talk about a couple of features that I think are important. D-branes arise as loci where open strings end, and that's enough to determine their kinematics and their dynamics entirely. You don't have to input any further information about D-branes into the theory. They're not put into string theory by hand. They're actually in the spectrum of the theory as non-perturbative objects. In units of the string scale, they have a tension that's proportional to the inverse of the coupling constant of string theory. So when string theory is very perturbative, D-branes are very heavy. But if you're BOD and you can turn up the coupling constant, you'll find out that if the coupling constant is really high, then D-branes will be lighter than strings. And the key fact for spacetime applications about a stack of D-branes is that if you have a large number of them, then distance scales that you might think were Planck scale or string scale can get parametrically enhanced to be as big as a black hole horizon. And the technical reason for that is if you write down a classical spacetime using supergravity and string theory with branes in it, the open string correction scale is not just the coupling constant of string theory, GS. I don't call it G sub string, because if you say G string, people laugh. So I'll just call it GS. And the thing is that, for example, the curvature, the warping in the spacetime produced by a stack of D-branes is controlled by GS times n. So if you have the coupling constant to be set small, but n is parametrically large, then you can develop very large amounts of space-time warping from having a large number of D-branes. And that's really what enabled Strominger and Vafa to build a model using D-branes that allowed them to compute in 1996 the first, first principle statistical mechanics calculations of the Bekenstein-Hawking entropy, SVH. You can call it black hole or Bekenstein-Hawking according to taste. So similar methods actually correctly account for the entropy even for rotating and near-rotating black holes in 4 and 5 dimensions, but still we haven't yet managed to reach the holy grail of making you a microscopic string theory model using world-cheap tools and other aspects like ADS-CFT. We still haven't managed to build you a believable model of the Schwarzschild or the Kerr black hole in 4 dimensions. That's kind of the overall goal, but we're able to do close to supersymmetric or supersymmetric ones with a great deal more technical force. But morally, if we want to do more than just count the entropy and solve the information problem, to learn about the degrees of freedom of quantum gravity and why black holes don't swallow information, then you need to know more than just about the entropy. You need to know something morally about the wave function behind the horizon. And string theorists with this business of building microscopic models of black holes actually got a lot further than computing the black hole entropy. We were able to model Hawking emission from classes of near-BPS black holes by using microscopic calculations of open string scattering and closed string interactions, and this yielded gorgeous agreement with the Hawking emission for entire classes of these near supersymmetric black holes, including gray body factors, which could depend on, say, 6 variables, and you get the full functional form from the string theory story. So string theorists didn't just build a Lego model of a black hole. We were able to work out how Hawking emission would work and see how ergo regions arise and so forth. So Samir Mathur made a very important conjecture in 2001 that was motivated by the treasure chest of new solutions that I mentioned and successes with string theory emission rates, that a conventional black hole geometry emerges as a coarse graining over things he called microstates. Another word that string theorists use to talk about these objects are fuzzballs. And what they are is non-singular, horizonless, so they don't have singularities and they don't have horizons, and they're not spherically symmetric. These microstate geometries have the same asymptotics as a black hole, but differ from them inside a region of order the horizon size. And this is sort of a bit of a top-down point of view of building black hole models, if you like, in string theory. We know about microstates. We understand things about their quantum theory. They're very complicated in terms of the gravitational fields that they give rise to, but we have better theoretical control over those. And you think of those as the microstates as like our Lego blocks. We're going to use the microstates to build you something that looks a lot like a black hole. And the big question is to see exactly how that space-time emerges from doing the coarse graining on those quantum gravity objects. again, which don't have a singularity and they don't have a horizon. These fuzzballs have an exponentially large density of states, and the physics is actually really interesting, but I don't have time to get into it, and if you want to learn about it, the man himself has a very nice fuzzball fact on his website. So to get back to that theorem, the one that says just fiddling around with semi-classical physics and corrections isn't going to resolve the black hole information problem. But what assumptions did he use? He used two very big ones. One of them was that the Hawking pairs, when they're created fresh from the vacuum, they're created independently of the other pairs. That was Hawking's assumption. He left it in because that characterizes the Hawking radiation. His second assumption was about a property of quantum gravity. But he did not assume what kind of quantum gravity it was. He didn't pick string theory. He said, you know, it could be any quantum gravity theory. But he said that theory does have to obey something called strong subadditivity, which is an information theoretic property of every reasonable quantum field theory that we already know and use. Mathur also helped clarify that a thing that confused several string theorists for a few years, which is that just having an ADS CFT duality in which you can create ADS black holes and have phenomena with them, just having the duality doesn't actually resolve the black hole information in principle. So this is something that you may not have known about this program, and I think that's physically very relevant and important.
Okay.
Yes?
What was the theorem? Sorry if I wasn't listening.
Mathur's theorem?
Yeah.
It proved that you can't resolve the black hole information paradox by starting from semi-classical spacetime and then doing perturbative corrections about that. So he was saying you need some order 1 kind of corrections. You need to use non-perturbative objects in your analysis to be able to resolve the information problem, even in 4 dimensions. And that theorem is not assuming 10 dimensions or 4 dimensions or anything. Just it's a very basic little, it's very easy to read, so in fact I can recommend the paper. Okay, so just a very brief commentary on some of the work that I do. It's concerning the, in fact I could just skip this part because it may not interest the rest of you so much. But the D1, D5 system is one of the string theory systems that is the best developed, and currently it's been something I've been working on with some graduate students and a postdoc who've moved on to faculty positions and postdocs and so forth themselves. But it's a prototype microscopic model, if you like, the easiest Lego set that we can use in string theory. And it's, you take a number N1 of D1 branes, wrap them on a circle, take a bunch of N5 branes, N5 of them, wrap them on that same circle times a 4 manifold. And the key thing that allowed Strominger and Vafa to do their computation is that this system has a moduli space. At one point, the theory is best described by black hole geometry, and at another point, the system is best described by a 2-dimensional conformal field theory, which is a symmetric product orbifold. And the thing that Strominger and Vafa made use of is that it's easy to calculate in this conformal field theory at this orbifold point, because it's actually a free theory. So you can just do a free field theory calculation for statistical mechanics, and that's all they did to produce the black hole entropy. So you might wonder, why is the black hole entropy of a set of D-branes, why is that equal to the black hole entropy? And the answer is that they had a supersymmetric non-renormalization theorem that protected the entropy, that says as you move around in moduli space, the entropy that you compute at the orbifold point will be the same as the entropy that you compute at the black hole point. So that's why Strominger and Vafa were able to say that they had honest-to-God computed the entropy of the black hole. But they didn't do it by actually working with the black hole. They used a physical, a mathematical convenience to be able to say, this is where we can calculate it, and let's then say, by the non-renormalization theorem, coming from supersymmetry, that that's why they could get the entropy right. But morally, if you want to honestly connect with macroscopic black hole physics and trying to get out general relativity and solve the information problem, you need to deform away from the orbifold point in modular space and go towards the black hole. This is a very top-down sort of framing, but it's one of the foci of our particular research. And the really key question from this story of string theory Legos for building black holes is how you see emergence of the effective black hole geometry. So now I want to talk about a fun thing, which is firewalls. You've probably heard a little bit about this. Hawking pairs that are created straddling the horizon, as they're created, they're maximally entangled. Their entanglement entropy between them is log 2. Now there's something from gravity theory in the 80s called Page's theorem by Don Page about the entropy of a quantum subsystem. And this describes how the entropy entanglement entropy between the black hole and its Hawking radiation isn't there at the beginning because the black hole only just formed. It grows as the black hole radiates, but it has to go back to zero again by the time the black hole evaporates, because then there won't be any black hole to be entangled with radiation. So his argument was that new Hawking radiation coming outside the black hole should be maximally entangled with the older Hawking radiation. The trouble is that these two things can't be true at the same time. You may know about quantum entanglement that you can't be maximally entangled with one guy and maximally entangled with another guy. It's a bit like trying to commit bigamy. You can't really photocopy yourself. That would violate the linearity of quantum mechanics. You can't solve the problem of trying to be maximally entangled with two different people and have two different marriages and two different families and all that sort of stuff. You can't just Xerox yourself. Because if you could Xerox every quantum state, that would violate the linearity of quantum mechanics. So you may have heard about something called all black hole complementarity, which finessed this bigamy issue by arguing very cleverly that black hole blue shifts prevent experiments from seeing violation of theorems that we know shouldn't be violated. So what did Almari, Maroff, Polchinski, and Susskind talk about? They, in 2012, pointed out flaws in this argument about all black hole complementarity and ignited this firewall debate about how effective is general relativity as a theory around black holes. Can we really trust it? If the geometry is not particularly strongly curved for a big black hole, why is it really the case that we can trust general relativity to tell us what the physics is? And so they had four postulates. One, that there's a unitary S matrix. Second, that effective field theory works outside the black hole horizon. The third postulate was that the black hole appears to a distant observer as a quantum system with discrete energy levels. And the fourth assumption was that nothing bad happens at the horizon as somebody falls into the black hole. If it's a big, big black hole, as you fall through the horizon, since the curvature invariants are small, physicists believe that nothing really bad should really happen. Well, when they did their technical argument just about excitation of field modes and for inflowing people versus outgoing Hawking radiation, it's just a calculation involving some Bogolubov coefficients. And their result was that one of these postulates, 1, 2, or 4, has to be false. They weren't willing to give up on 3. That's why they didn't say, didn't include 3 in the list. So they believe, all the people who wrote the AMPS paper, believed that the second assumption, that general relativity should be a good approximation outside a big black hole. So they said, well, in that case, if 2 is true, and I don't want to give up unitarity because I want to solve the black hole information paradox, then I'm stuck with the fact that it's not true that nothing bad happens at the horizon. So they postulated that actually what happens, according to the rules of quantum mechanics, is if you try to fall into a black hole, it should burn up in a conflagration. So that was why they said that there were firewalls. What a firewall is according to a person who falls through, if general relativity really is true as an effective field theory around black holes, then they concluded that everybody who falls into the horizon gets burned up before they can even cross the horizon. And that's a bit strange, right? A lot of people have been really upset by this idea that there are firewalls, and they've tried to do anything they could to get around it. Yes?
Number 4 is, isn't it basically assuming the equivalence principle?
Yes, that's right. So the equivalence principle doesn't seem to be correct for informing people. And that's very counterintuitive for somebody trained in general relativity. So
that's number 4. That.
Nothing bad happens at the horizon, that's the assumption. And it has to be false if you believe in effective field theory. But I would rather give up postulate 2. I'd rather say, I don't particularly want to burn up in a firewall. I want to be able to understand how things happen, but then that means that general relativity is not the approximation that you can also use. That means you have to go to full string theory to be able to understand the equations in the black hole information paradox. Stephen Hawking hated the idea of firewalls so much that he wrote a paper saying he would rather give up on event horizons. And if you're interested in the firewall controversy, there's actually a really good substantial review article by Daniel Harlow that is about the black hole information paradox, but includes discussions of firewalls. So what have people tried to do to avoid firewalls? Harlow and Hayden made a really interesting observation that according to quantum information theory constraints on being able to just actually get information out of a black hole, they probably prevent firewalls. And aspects of this were explained more intuitively by in a Susskind paper that was a companion paper to that one. Giddings tried to entertain an idea of introducing a small, what he called a non-violent amount of non-locality to save you from firewalls. The technical challenge there is generally very difficult to only introduce a small amount of non-locality theoretically. If you introduce a bit of non-locality, it tends to spread everywhere because gravity spreads everywhere. Mather and Turton explained the advantages that fuzzballs have in evading firewalls. So if you take this top-down point of view, that we're building black holes by building microscopic models from the top-down perspective and then trying to move them towards the classical objects that we know and love from general relativity. And other people have even gone as far as entertaining having state-dependent operators in their conformal field theory. A lot of people think this is very controversial and its status is quite murky, but it gives you an idea of just how desperate people are to avoid this firewall problem. And Maldersen and Susskind propose a new take on this, and they basically use an old idea of Israel involving something called the thermofield double state. And their essential idea is that entanglements are encoded by having non-classical wormholes. So they're little quantum wormholes that help us to feed the entanglement in the right directions in the physics of black holes. And they have the idea that the length of the little bridge, the wormhole, is inversely proportional to the entanglement. So if you have weak entanglement, that would sort of be a long, spindly Einstein-Rosen wormhole. And if you have a very strong entanglement, it would be a short, fat one. Yes?
So in the previous slide, you mentioned Gidding's suggestion of small non-locality. If you introduce small non-locality, isn't it equivalent to dropping both number 2 and number 4 before in the previous list? Because somehow you need the...
Well, he was trying to avoid 4, so that wouldn't have been a setup.
No, I mean, it's fine. I just want to understand. So introducing some non-local terms would break also the usual setup for effective field theory for gravity and field. So you're actually removing both.
I think it's a violent choice.
No, I actually like it, but I'm only pointing out that it's removing both things, not just one of them.
That's true. Well, it's certainly removing 2. I don't know that I would agree that it's removing 4, because he was trying to avoid firewalls by doing it.
Well, if it is, something, if 4 is really like an equivalence principle assumption, then I'm not even sure how to formulate the equivalence principle if I'm not in a local context. What do I mean that locally I become Minkowski or
Yep. All good questions. But since I'm running out of time, I need to just say a couple of things about holography. Let's see. What I want to do is to sort of extract out in the next 10 minutes is a little bit about the reasons why string theorists think that classical geometry is related to quantum entanglement. And that might seem a bit controversial as well, because why am I saying that classical spacetime could come out of quantum entanglement? How could that be? One of them is classical and one of them is quantum. And the reason is that it makes use of the ADS-CFT duality. And the ADS-CFT duality is a strong-weak duality, which says that when the ADS is strongly coupled, the CFT is weakly coupled. When the CFT is strongly coupled, the ADS is weakly coupled. So weak coupling means classical, and strong coupling means very quantum mechanical. So that's the reason why we suspect that there are very strong linkages between quantum gravity, at least in asymptotically anti-de Sitter space, and the properties of these field theories. So, as you may know, ADS-CFT holography arose from studying stacks of D-branes. In fact, Maldersen's derivation of it started with a stack of D3 branes, and then he said, well, because I've talked about that parametric enhancement story, I know that branes can give rise to significant gravitational fields. And if you concentrate on the very near to the brane stack, you discover that the geometry of that space is actually ADS5 times S5. So that's where the ADS came from in the ADS-CFT correspondence. So where did the conformal field theory come from? Well, if you take a stack of D-branes and you look at it from an open string perspective, there are the lowest modes that are available for open strings have spin 1 and 0 mass, and that's why the theory that lives on a world volume of stack of n D-branes is supersymmetric Yang-Mills theory, plus some alpha prime corrections and some string corrections. So Maldersen took a very clever low-energy decoupling limit of that stack of branes, in which case he got on one side that the closed string description of this was ADS5 times S5, which is a quantum string theory. And also that he looked at it from the perspective of the field theory living on the branes, which isn't living in 10 space-time dimensions, it's living in 3 plus 1 for the free branes. And he discovered that that low-energy limit just produced the Yang-Mills theory and no corrections. That's the idea of taking the special decoupling limit. So that was how he derived the ADS-CFT correspondence in the beginning, by staring at the physics of a stack of branes. As I said, we don't know how to do the worldsheet analysis for this, but we've got ADS-CFT dictionary, And people have applied this to things as broad as modeling the quark-gluon plasma and, as I said, condensed matter with limited success. The interesting thing from the condensed matter perspective is you can calculate transport properties, so Lorentzian properties, not just Euclidean properties of the field theory. And the physics is very different in spirit to the story of quasi-particles. There's also a DSCFT, the correspondence that's being developed to try to address cosmological questions using holography. The downside there is that you have to use a non-unitary conformal field theory. So the physics of that is really quite different, but it's being developed pretty well. And I'll just make one sort of structural comment that Maldesen's construction, this conjecture of holographic equivalence between these two systems, the two systems are different ways of looking at the physics of the same stack of branes, that it gives us a definition of Lorentzian quantum gravity in asymptotically anti-de Sitter space. The way you do it is, well, you say that Euclidean CFT, Euclidean quantum gravity is dual to Euclidean field theory. Then we rotate in the field theory, which we know how to do because it doesn't involve gravity. And then we say Lorentzian field theory is equal to Lorentzian quantum gravity. So that's how we get a definition of Lorentzian quantum gravity in anti-de Sitter space. Now there's a whole bunch of stuff about the holographic dictionary which I really don't have time to talk about, but I will say one thing. It conjectures that the partition functions of the theory are equal, and it talks about some details about how things match up. There's a dictionary between a field in the bulk and something on the boundary. And, for example, the graviton in the bulk is dual to the stress tensor of the boundary theory. You find that there are different probes that you can use to analyze the holography. And what you can do is to study local operators. Then you can study, like, for example, a graviton, or you can study an open string. And you find that there's a correspondence between where you are in the bulk, in the radial direction, and what energy you are in the field theory. So, in fact, if you go to high energy in the field theory, that corresponds to going out near the boundary of anti-de Sitter space. If you run down in energy in the quantum field theory, that corresponds to going into the interior of the bulk. And people were even able to write down a whole story of the holographic renormalization group, understood by using equations in the bulk written in the Hamilton-Jacobi form for evolution in radius. And people were even able to get out counter terms that are necessary for surface terms that you need to chase when you're doing gravity in anti-de Sitter space. So they also looked at non-local probes like correlation functions and found that for certain protected states under supersymmetry that you can get exact agreement of 2 and 3 and higher point correlation functions. And people used Wilson loops and entanglement entropy and learned how to connect what you do for the field theory on the boundary with propagators and vertices in the bulk. And the key thing about ADS-CFT, it shows us how one extra bulk space-time dimension emerges, but at present there is no path integral proof, except for some particular kinds of holographic systems. For ABJM theory of this n equals 6 supersymmetric theory of multiple M2 branes, people were actually able to prove the duality at the level of path integral. You could prove that the path integrals were equal using some fancy mathematics called supersymmetric localization techniques, which have been all the rage in string theory in the last small number of years. So people were actually able to prove for some limited classes of the ADS-CFT dualities, prove it at the level of path integral. So for those systems, it's not a conjecture, it's proved. Pretty fancy math, but it's pretty neat. So that's ABJM, which has been one focus of holography. Geez, I'm really running out of time, I'm sorry. I practiced this last night and it went much faster. ADS-CFT does shed light on the question of background independence because it's independent of the bulk background, except for the fact that the asymptotics have to be locked down by the boundary physics. So that is a concession that we have to make, but modulo that concession, the physics in the bulk is entirely quantum gravity. You need to model real-world systems as a physicist, and you need to break increasing degrees of symmetry. There's a lot of literature on this, but the essential idea that's interesting to a gravity theorist is that you can geometrize phases of the dual quantum field theory by just using things that you know about gravity solutions. It's been one of my foci in research. Yeah.
So I'm sorry, because I lost the passage. So when you were talking about the
Which slide do you want?
The DS-CFT correspondence,
that one?
right? Yeah, the DS-CFT. Yeah, right. That's one. So and you say that works. It's a program that works quite well. You were thinking in the context of string theory or
the de Sitter
right.
correspondence. Well, I don't know if we really know how to embed that one in string theory.
That's what I was asking.
Right.
Okay,
We do know how to find ADS CFT as a
it's
limit
a
of string theory.
conjecture which has, in principle, no inputs from string theory. The way in
That's
which
really
that
true. What
right.
people thought was, I see ADS CFT, I see a lot of technology that looks really cool, and
Yeah.
maybe if I tried it for the Sitter space, even
Yeah.
though my CFT is
But
non-unitary.
They found something at a certain point. So you are right. But I just wanted to understand when you say that it works well, if you were referring to the couple of cases.
Yeah.
Because they found a couple of supergravity solutions out of the CFT. But yeah, okay. But
It's not, DSCFT is not nearly as well developed as
exactly,
ADS CFT.
exactly. No, I just
But
wanted
one
to
person
make
who's
sure.
done some very nice work on that is Tom Hartman.
Yeah, okay.
So,
I wanted to understand whether you were referring just to the context of string theory, or you were referring to the conjectural correspondence, which in principle has no inputs from string theory.
right, but it was actually derived by staring at stacks
Yes,
of D-branes.
absolutely.
I mean, that's where it
Absolutely.
came from, but the conjecture could have been made years earlier
Exactly.
if somebody had just put the pieces
Exactly.
together.
Yeah, yeah.
It was always there, the correspondence. We just
Yes.
didn't know about it until late 1996,
Yeah.
7.
Okay, thank you.
Yeah.
Thank you very much.
So I'm just really conscious of the fact that my time is pretty much run out, but I still have a couple of interesting things to say, so I guess I'll rush through, and if somebody's interested in any of these things, they can ask me. Higher spin, as I said, might be a bridge between string theory and full string theory and just gravity, so this is a massless level, spin 2, spin 3, and higher. People had put stringent constraints on low energy scattering and flat spacetime that actually forbids massless particles with spin 2 greater than 2 from participating in any interacting quantum field theory, but that was in a spacetime with zero cosmological constant. And if you have anti-de Sitter space, a negative cosmological gap actually provides two things, a dimensional coupling and an infrared cutoff, which end up letting you in the end reconciling higher spin gauge symmetries, the gauge symmetries for all of these modes, with the equivalence principle. And this gives Mikhail Vasilyev's famous nonlinear unfolded equation of motions, incredibly technical, and this was the most accessible article that I could find, and I was still struggling with it a little bit, so higher spin is pretty technical. But people were able to find the dual theories for these ended up being theories of free fermions and free bosons, depending on the kind of boundary conditions you had to put on. And it's quite amazing that you can get CFT equals a higher spin theory and have a working correspondence that allows you to write down a holographic dictionary and compute correlation functions doing this. It was pretty amazing work. The ADS-4 one has been nicely reviewed by Jianbin Yin, and Gopikar and Gabadil were the ones who found the ADS-3 dual, which was to a minimal model with WN symmetry. That's why I was talking about the W algebras. But Gopikar and Gabadil, for the case of higher spin and ADS-3 being dual to a conformal field theory, actually got even further. They were able to prove that the higher spin, Vasilyev's higher spin theory in ADS-3 is actually a subsector of string theory, in particular in the tensionless limit. And this is a very interesting to people who work on the formal structure of string theories and quantization of gravity. The interesting thing is that this provides a proof for the ADS-3 case that this model is like a bridge between just gravity and full string theory, which is much more complicated about the levels and the masses and so forth. So higher spin theory in 3D also has black holes, ADS-3 black holes, and the existence of horizons and singularities is not invariant under higher spin gauge transformations, but you can still define a black hole via the holonomy and gravity if you use the Chern-Simons formulation of 3D gravity. And that's been some very pretty stuff that's come about in the last 2 or 3 years from the higher spin story. There's also a whole load of interesting stuff about trying to localize stories in the bulk using the ADS-CFT correspondence. And one of the important people who first conjectured this link between classical space-time geometry and entanglement in the boundary field theory that it's dual to was Mark van Ramsdonk, who conjectured back in 2009 and 2010 that this was coming. And people think that entanglement entropy, which is really interesting quantity to look at, might not be enough to probe the bulk geometry. But other people have argued recently that localization of information in the bulk, which we want to understand if we want to understand how quantum gravity really works, maybe this should be actually understood in terms of quantum error correction in the quantum field theory, things like quantum secret sharing protocols and so forth. And lastly, just finishing up, there's been a huge focus in the last 5 years, but especially in the last 2 or 3, on the role of entanglement in holography. And the basic idea is that you have some theory that lives on the boundary up here, and you could ask if you have some patch A here, and some other patch B in your field theory, you can calculate the entanglement of these things using quantum information theory. But what you and Takiyanagi discovered is that you could measure this entanglement also in bulk by using the area of the minimal surface that connects those patches on the boundary. And so what string theorists have been able to do is to geometrize the story of entanglement. And there's even physics of soap bubbles that if you get the patches too far apart, then it's more energetically favorable to have two little soap bubbles rather than one big U-shaped soap bubble. And you can show that that the quantum information theory constraints on what patches do and how, if you double the size of the patch, a lot of quantum information stuff can be fully geometrized using the stuff of minimal surfaces in bulk. So this is what I mean when I say that string theorists are getting increasingly convinced that space-time geometry and quantum entanglement are very much, the different sides of the same coin. And in the case of ADS CFT, we have explicit stories that really show us how that's happening. Now, I want to make caveats that it's not just that, if you talk about entanglement, you can suddenly make a big, fat, semi-classical space-time that has all the properties that you want. It's not clear whether the entanglement is enough. Maybe you need spectral information about the theory also to diagnose space-time connectedness. So this is hints at the present time, and I find them quite convincing, but there needs to be much more work done to make this very convincing. So that's just a rough summary of what I talked about. Thank you for being patient with me.